we were talking about a contingency table. But before we actually talk about the contingency table, there are a couple of questions on the Module 2 handout number 2. And that handout, okay, for Module 2, Part 2, questions number 3 and number 5. Okay, we want to take a look at number 3. We'll take a look at number 5, and then we'll talk about the contingency table. Okay, and that'll sort of wrap up the first part of Module 2. And then we'll look at the second part of Module 2. Okay, so what I have actually on the screen, this is from Module 2, Part 2. Okay, so there are actually some questions that are on Part 1 that are actually a Part 2. So just to revisit what we talked about, okay, in the last class, we talked about probability, and that probability is between 0 and 1, and 0 as a percent is 0%, and 1 as a percent is 100%. We talked about the notations for probability. We talked about the classical approach to probability, right? And the classical approach to probability is the number of ways an event can occur over the number of different simple events. And we kind of liken that to a fraction. If you think about a fraction is a part, like the part that we're interested in, over the whole, right, or the total amount of items that we're dealing with. We also took a look at independent and dependent events. So for independent events are events in which one event does not affect the other. Okay? And we talked about the lottery and choosing numbers and such. And then we talked about dependent events, right? And for a dependent event, one event is dependent upon another event. Okay, so one event happening affects the probability of another event. We talked about the fundamental principle of counting and the fundamental principle of counting. And these type problems were not necessarily asked for a probability, but were more so asked how many different ways something can happen, right? So we looked at license plates, we looked at social security numbers, and that was using the fundamental counting rule or the fundamental counting principle. Okay. Now, as far as the classical approach to probability and this fundamental counting rule, we're going to take a look at problem number 3. Okay, and this is from Module 2, Part 2. All right. And it says that, I believe I have it on OneNote. Here it is right here. Okay. A quick quiz consists of multiple choice questions with 6 possible answers followed by a true-false question, right? So there's 2 questions on this quiz. The first question is multiple choice, but it has 6 answer choices followed by a true-false question, right? If both questions are answered with random guesses, find the probability that both are correct. You may answer with a fraction or a decimal rounded to 3 decimal places. All right, so we're going to close that down. All right, we're going to map this out as far as the outcomes are concerned. So in this problem, it's a combination of the fundamental principle of counting as well as that classical approach to probability. Right, so I'm going to map out 2 outcomes. Right, so this would be for the first question. Right, we're going to find its probability of a correct answer. And then we're going to map out another outcome, and that's for the second question. Right? So I have two outcomes or two questions. So this is the reason for the two blanks, right? So now we must figure out the probability of the first question being answered correctly, right? So if we think about the classical approach to probability, what's going to be my denominator? So what I mean by that is how many answer choices are there to choose from? 6, right? So the denominator is going to be 6. Out of those 6 answer choices, which or how many would be correct? Just one, right? So the probability of guessing the first answer correctly is 1 out of 6, right? Because there's 6 answer choices, only one of them is correct. So that has a 1/6 probability. Now we're going to figure out the probability for the second question. So again, I'm going to start with the denominator. So how many choices do we have for a correct answer? 2, right? Because it's true or false. And out of those 2 choices, how many is correct? Just 1. All right. So this is an example of using both the classical approach to probability, right? Because we use the part over the whole, so to speak. And then we're mapping this out as far as the fundamental counting principle. So in order to figure out the probability, we're going to multiply the numerators. We're going to multiply the denominators. And we have our probability as 1/12. All right, so any questions about number 3? All right, next we're going to take a look at problem number 5. Right, and again, this is from Module 2, Part 2. And problem number 5 on Module 2, Part 2, it reads that 5 distinct 5-sided dice are rolled. Right, so we talked about the die is singular, which means one die, and then dice is plural. And we also talked about it if it's not mentioned that it's something other than a 6-sided die, right? If they just say a die is rolled, that's just your standard 6-sided dice. In this particular problem, they're using a 5-sided dice. 5 distinct means that there are 5 dice, right? Each one is separate. I'm not taking the dice and rolling it 5 times. I have 5 dice in my hand, and each one has 5 sides, and I'm rolling them all at one time. Now, are these dependent or independent events? So even though I'm rolling all the dice at one time, does one dice affect another dice? It doesn't, right? So these would be independent events. Since we have 5 distinct dice, I'm going to map out 5 outcomes. 1, 2, 3, 4, 5. Right, I'm going to map out 5 outcomes, okay, because these represent the 5 dice. So this would be the first dice or die, the second die, the third die, the fourth, and the 5th. Okay. So now notice this is not asking for a probability. It's asking for how many outcomes are possible. So whenever you see this, how many outcomes are possible, you should think, or one of the things you should think is this fundamental counting principle. We're going to look at some other things in the next part where you're going to see these same type questions, but you're not going to use the fundamental counting principle, right? But anytime you see how many different outcomes, this is what you should think first, okay? And then see if your problem fits this criteria, okay, for mapping out outcomes. All right. So now that we have 5 outcomes mapped out, how many choices do we have for the first die? 5, right? Because it could be the numbers 1 through 5 or whatever they're using on those faces. So that's going to be 5. Also, for the second die, how many outcomes? 5. Okay. There's actually going to be 5 outcomes for each of these 5 dice. So in order to determine how many different possible outcomes, we're just going to multiply all these together. All right, so that's 5 to the 5th power. And I believe 5 to the 5th power is 3125. But if you're using the calculator, right, I'm going to take 5 and I'm going to raise that with this caret or exponent key. We're going to raise that to the 5th power, and we have 3,125 different possible outcomes. All right, so any questions about 3 or 5? All right. So now let's look at the contingency table. Still part 1, okay. So now a contingency table is a table of observed frequencies where the rows correspond to one variable classification and the columns correspond to another variable of classification. This is also called a two-way table. So looking at this contingency table, notice that the rows, right, the rows go across, and for the categories for our rows, we have gender, either male or female. Right? There's also row totals, right? So there's 82 males in this contingency table, and there are a total of 54 females. Altogether, there are 136 people in this particular contingency table. As far as the columns are concerned, the variable of classification for the column is a letter grade, A through C, right? A, B, and C. And if you look at the columns, notice that there are also column totals, right? So there are a total of 60 A's, 42 males made A's, 18 females made A's. There were a total of 62 B's in the course. 34 males made B's, 28 females made B's. And then there are a total of 14 C's in the course. 6 males made C's and 8 females made C's. Notice that the column total and the row total are exactly the same. There are 136 people, and then there are 136 grades, right? A, B, and C. So from this contingency table, we can pull out probabilities. All right, so I'm going to go into OneNote. All right, so this is the same table from, let me shrink this up slightly. All right, this is the same table from the lecture note. All right, so we're asked these following probabilities. It says if one student is chosen at random, answer the following probabilities either using a fraction or a decimal rounded to 3 decimal places. All right. So A says find the probability that the student received a B in the course. So we're going to set these up using the classical approach to probability, right? Like into the fraction. The part that we're interested in. So in this case, the part that we're interested in are every student that received a B divided by the total, right? So let's set that up as a fraction. So now I generally like to start with the denominator first. So how many people are we looking at for this particular probability? Okay, well, that's right. The top number is 62, right? Because if I look at all of the B's in the course, there were a total of 62 B's. And there were a total of 136 total grades. So my first probability is 62 divided by 136, which is 0.456. So just keep in mind, if you wanted to answer it as a fraction, that fraction would have to be in lowest terms. So just to quickly review how to convert a decimal to a fraction using the calculator. All right, once you have your number decimalized, you simply hit math. The first option says that it'll take what it's given and it will try to convert it to a fraction. So I'm going to use this first option. And if I hit it again, I get 31 over 68. All right, so you don't want to use that decimal rounded to 3 places or the fraction in lowest terms. B says on the probability that the student is a male. So how many males are in the course? 82, right? Divided by all of the people in the course, which is 136. So 82 divided by 136 is 0.603. All right, so any questions up to this point? Okay. C says find the probability that the student was male and received a B in the course. Right. So the student was male. There were 34 males that received a B. All right, divided by, and how many people are in the course? 136, right? So that's 34 divided by 136, which is 0.25. All right, so now for D, D is written out a little bit different because it has this special word in it, given. It says find the probability that the student received an A in the course given they are female. So now we haven't seen the word given up until this point. Whenever you see the word given, that restricts your denominator, or that restricts the total amount of people that we're looking at. So in this particular problem, we're not looking at everybody. We're only looking at the what? Females. So how many females were there in the course? Right. There are a total of 54 females. So 54 is our denominator. All right, so we're no longer using 136, right? Because for this probability, we're asked if they received an A given that they were female. So our denominator is restricted to only females. And out of those only females, how many received an A? 18, right? So that probability is 18 divided by 54, which is 0.333. So anytime you see the word given, your denominator is limited to only a certain category. Okay, in this case, only the females. All right, so let's look at E through H. All right, so E says find the probability that the student is female given, so that's that restricted denominator again, given that they received an A. So what is our denominator? Well, it says given they received an A in the class.
You still gotta
go with females. The total amount of people that received A's were 60, right? So our denominator here is 60, right? Okay. Find the probability that the student is female. So how many females received A's? 18, right? So that probability is 18 divided by 60. Okay, I thought I was hearing a video in the background. So 18 divided by 60 is 0.3. F says find the probability that a student is female and received an A in the class. I don't know why that keeps happening. All right, so find the probability that the student is female and received an A in the class. So notice that there is not that special word given. So our denominator is what? Well, it's going to be everybody in the study, right? 136. And for my numerator, I have to locate females that received an A. So the total number of females that received an A is 18. Right, so that's 18 out of 136, which is 0.132. G says find the probability that the student received an A given they are female. That's actually number D. That was a repeat. All right, those are the same question. All right, so that's 18 out of 54. Which was 0.333. And then the last one says find the probability that the student received an A and they are female. All right, so there is no word given, so we're using 136 as the denominator. And then if we look at the table, we want females that received an A, so that is 18, right? So we get 0.132. So you'll notice like a lot of these questions, they look the same, all right? But if you do not see the word given, then your denominator is going to be the row column total. Anytime you see the word given, you just want to make sure that you restrict the denominator based on what's after the word given. All right, so any questions about this contingency table? All right. All right, so there was no like fundamental principle of counting or anything involved, just sort of mapping out the fraction, basically, the part over the whole. All right, so now we're going to get into the second part of Module 2. All right, first is the addition rule. So it says to find the probability of event A or event B occurring. So now we've seen this word or before. It was like with the pencil, find the probability that the pencil is red or orange. And we did something totally different than what we're doing now. Okay, so I'm going to kind of explain the differences between the two. We begin by finding the total number of ways that A can occur, the total number of ways B can occur, but we find the total without counting any outcomes more than once. So it's like you see this formula. It says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. So now here's an example. It says at MUSC, it was found that 72% of the students are taking Spanish, 78% are taking English, and 66% of the students are taking both. Find the probability that a randomly selected student is taking a Spanish or an English class. Answer, you may answer as a fraction or a decimal rounded to 3 places. All right, so this is that same example. All right, so I'm going to use the addition rule. Okay? And this is why, because they only want to know how many people are taking Spanish or English only. So if you're taking Spanish and English at the same time, we have to subtract that probability out. All right, so this says that the probability of A or B, that's equal to the probability of A plus the probability of B minus the probability of A and B. So if I kind of liken this to our problem, A is going to be the students taking Spanish. B is going to be the students taking English. All right, so if I just kind of substitute into this little formula, that's the probability of students taking English plus the probability of students taking, I got this backwards, let me just write it right. That should be Spanish plus the probability of students taking English minus the probability of the students that are taking Spanish and English at the same time. Okay, so I just kind of written that out in words. So they give us the probabilities in the problem. So the probability or the percentage of students taking Spanish is what? %, right? So I have to convert that to a decimal. So that's 0.72 plus the probability or percentage of students taking English, which is what? 78%. So that's 0.78 minus the probability of students taking English and Spanish, which is 66%, which is 0.66. So if I simplify 0.2 plus 0.78 minus 0.66, we get 0.84, right? Which is 84%. So it's a highly likely that if you randomly select a student that they're only going to take English or Spanish. Now, we actually did see this OR thing earlier, but we didn't use this formula. So I just wanted to show you why we didn't use it. If I scroll back through it was an OR problem somewhere. Where was it? It was with the pencils. It was this one, number 2. And this is from Module 2, Part 1. And it's to the word OR, orange or red pencil. So what we did was there were 30 pencils all together in the bag or in the jar. 7 were orange, 6 were red. We didn't subtract anything, right? This is the reason we didn't subtract anything, because in the bag, there are no orange, red pencils. So like if you had red pencil, you had orange pencils, and then they had like some striped pencils that were orange and red. If that were the case, then we would use this addition rule. Okay. So I just want you to see the difference on when you use this minus thing and when you don't use it. The only reason we're using minus here is because there are some students that are taking English and Spanish at the same time. Okay, so we have to use this addition rule.
I guess combining the A and B problem.
That's right. Okay. That's right. You have to take out the overlap, basically. Okay. All right, now we're going to take a look at factorials. And a factorial it denotes the product, and product means to multiply, of decreasing positive whole numbers. For example, 4 factorial, that's equal to 4 times 3 times 2 times 1. And if you multiply those 4 numbers together, you should get 24. And by special definition, 0 factorial is 1. All right, but notice when you're calculating the factorial itself, you never use 0, but 0 factorial is 1. So I'm going to show you where you can find these factorials in the calculator. So if I go into math, and if I scroll over to probability, that PRB is probability abbreviated, the second, third, and fourth functions are the functions we're going to use in this class. The fourth function is a factorial. The second function, where you see NPR, that is called a permutation. And NCR is a combination. All right. And then symbol number 4, function number 4 is a factorial. All right. So if I go back to my home screen, I'm going to calculate 4 factorial. Right, so you want to put all your calculations on the home screen. So if I hit 4, and if I go into math, if I scroll over to probability, and if I choose that factorial, right, it kind of spits it out. 4 factorial is 24. Right, and it also recognizes the special definition that 0 factorial is equal to 1. All right, so that's just the fact all across the board. Now, we don't really use factorials per se, but there is an example that kind of illustrates the use of a factorial. And it's this example with the Spiderwick Chronicle books. It says Bradley owns all 5 books in the Spiderwick Chronicles series. In how many different orders, so this is how many different ways again, can he place all of them on the top shelf of his bookshelf? All right, so let me just find that problem. I believe it is here. All right. So based on what we just did, whenever we see this, how many different orders, we should do what? Use that fundamental counting principle. All right. So since we have 5 books, I'm going to map out 5 outcomes. 1, 2, 3, 4, 5. All right, because it wants to know how many different orders. Right. So we're going to learn something else about how many different orders, but for now we're looking at this fundamental counting principle. So for the first outcome, that's the first book on the shelf. The second outcome is the second book on the shelf. Then the third book, the fourth book, and then the fifth book, right? Okay, so we're kind of mapping that out using the fundamental counting principle. So over here, I'm just going to draw 5 books. 2, 3, 4, and 5. All right, so say these are the Spiderwick Chronicles. I don't even know if that's a real book or not. I keep saying I'm going to look it up. I use it every semester. But all right, so I have 5 books. How many choices of books do I have to choose for my first book? So say we got 5 books over here. This is our top bookshelf. I can choose how many of these books to put first. 5, right? I got 5 choices. So let's just say I choose that one. For my second book, I now have how many books to choose from? 4, right? So let's say I choose that one. For the third book, I have how many choices now? 3. So let's say I choose that book. For the fourth book, there are how many books left to choose from? 2. So let's say I choose this one. And then for the last book, how many choices? Only 1. So the concept illustrates that fundamental principle of counting on top of the factorial deal. So if I multiply all these things together, right, 5 times 4 times 3 times 2 times 1, I get 120. Or if you recognize that that's a factorial, you can all put in 5 factorial and still get 120 with less numbers to punch into your calculator. Right. So now as far as factorials are concerned, this is about far as it goes with the factorials that we're going to calculate. Okay. All right, so any questions about that example?
It's a movie.
Is it? Okay, you seen it? Is it good? Okay.
It's produced by Nickelodeon, so it's a children.
Oh, okay.
It's almost like a
Harry Potter? Okay. All right, so now we're going to talk about permutations and combinations. All right. So now up until this point, when it asks for how many ways you can order something or how many combinations, the first thing we looked at was the fundamental principle of counting. The next thing you may want to look at, if the fundamental principle of counting doesn't fit the situation, you may want to look at what is called a permutation. So here is the permutation rule. It says that there are n different items available to choose from. we select R of the N items without replacement. So like in that Spiderwick Chronicle thing, once we took a book out, we didn't put it back into the mix of books, right? We let that book stay without replacement. It says we consider arrangements of the same item to be different sequences. The permutation ABC is different from the permutation CBA and is counted separately. Right. Here is a formula for a permutation, right? So if I kind of pull up the calculator, this is actually formula number 2, that NPR. So this formula that you see, n factorial divided by the quantity n minus r factorial, we never actually use that formula to calculate it. We will simply use the function in the calculator to calculate it. So it says that you are the casting director for a local production of the play Hamilton. There are 5 distinct parts available, but you have 18 volunteers. In how many different ways can the play be cast? All right. So for this example, we're going to use a permutation. Let me just write some stuff over here on the side for a permutation. Put it up in a little bit. In a permutation, the order matters. So here's some examples. Casting a play. So this is why the order matters when you cast a play, because when you cast a play, certain people can only play certain roles in the play. So like if you're doing Romeo and Juliet, you may not want a male to play Juliet. So it's a certain order to things. Whenever you see running a race, so like first, second, and third, how many ways can you place first, second, and third? You will also use a permutation because the order matters, right? You don't want to give a first place trophy to somebody who finished last type deal, right? It's the order matters. So whenever you see casting for plays and running a race, finishing first, second, and third, you should automatically think permutation. Right. So for permutation, it says, okay, you're the casting director for a local play Hamilton. There are 5 distinct parts, but you have 18 volunteers to choose from. And how many different ways can you cast a play? So N is going to be the total number, in this case, of volunteers, which is how many? 18 people to choose from, right? R is going to be parts available, which is going to be 5, right? So N is always the total, R is always how many you're choosing from that total. So if I write this out in permutation notation, it's going to be 18 permutate 5. So that's actually what I'm going to put in my calculator. I'm not going to use this formula. I'm going to simply just put this in my calculator, and the calculator is going to calculate the formula. All right. So again, I'm at my home screen. Right, put all your calculations always on the home screen. Next, I'm going to put in 18. So you must put in a total number first. Then I'm going to go into probability. and I'm going to choose NPR, and then I'm going to put in the number, in this case, the number of parts we're choosing, which is 5. So we have 1,028,160 different ways the play can be cast. All right, any questions about that? Now, when we're talking about permutations, a combination lock is not a combination lock. It's actually, it's called a combination lock, but it's actually a permutation lock. And this is why. Because the order that you put the numbers into the lock will unlock it. That matters, right? So you can't, even though you know the 3 or 4 numbers or whatever, you must put them in a certain order, right? So a combination lock is not actually a combination lock, it's a permutation lock because of that ordering. Right? So now we're going to take a look at combinations. So in a combination, the order does not matter. The combination rule says that there are n different items available to choose from. Okay, that doesn't change it. R is still the number of items that you want to select, and again, it's without replacement. It says consider the arrangements ABC and CBA to be counted the same, right? Because the order doesn't matter. So next we see the kind of convoluted combination formula is n factorial divided by the quantity n minus r factorial times r factorial. Okay. But we don't necessarily calculate this, right? The calculator is going to do it for us. We simply have to, first of all, be mindful of what we're dealing with. Either it's a permutation or a combination. Then we have to be mindful of the total things there are to choose from, and then we have to be mindful of how many things we're choosing. Okay. So here is the example. I'm going to go back to OneNote. It says the Houston Chippers is a local golf team which currently has 20 members. If only 6 people can participate at the same time and positions are not considered, how many different groups of members can be selected? So in this example, the order or the positions don't matter. So now if this part of the sentence was not in here, then it would be a permutation, right? Because if you're going to pick a center and positions matter, you're going to pick the tallest person. You're not just going to randomly pick anybody to be the center, right? If you're trying to pick a guard, you want to pick a person that can handle and dribble the ball, shoot and pass. You don't want to just pick anybody, right? But here it says positions don't matter. So that would constitute this as a combination. So now, since we've established the fact that it's a combination, what is N? N is going to be the total number of members, which is what? 20. And R is going to be the people that we choose to participate, which is 6, right? I'm going to just say participants, which is equal to 6. So I'm going to set this up as 20, choose 6. So if we calculate this in the calculator, I'm going to put in my total, which is 20. I'm going to go into probability. I'm going to use that third function. All right. And we're going to choose 6. So it's 38,760. people to choose from. 38,760 different possible combinations. Right. Yeah. All right, so any questions about a combination or a permutation? Okay, going back to the notes. Now we're going to shift from probability, and we're going to talk about a probability distribution. So we talked about a frequency distribution, and in a frequency distribution, that's just a table with nothing more than counts or tallies, right? For a probability distribution, it's a table of probabilities. Now, in a probability distribution, you're normally going to see two columns. So if I go to, I should have put an example of what one looks like. But on the Module 2, Part 2 handout, if I can find it, that very last problem, number 6, that is what a probability distribution looks like. Right? It's just two columns. The first column is a random variable. And a random variable is nothing more than a single numerical value. Right? So looking back at that example, right? So this is the random variable x, and it's just nothing more than a number. The second column are the probabilities. So like in this example, it says a local bakery has determined a probability distribution for the number of donuts that they sell in a day. So for 0 donuts, so that 0 is a random variable, the probability is 18%, 0.18. For selling 5 donuts in a day, it's 0.1. For 10 donuts, it's 0.17. For 15 donuts, we got to figure that out. And then for 16 donuts, it's 0.36. Right? So this is a probability distribution. It has, the first column is a random variable. The second column is the probability. Going to the last slide, here are some conditions or requirements for a probability distribution. The first requirement says that, and it's funny looking E, again, that is summation, and it means repeated addition. So it means that if you add up all of the probabilities in your probability distribution, it must equal to 1. So remember, 1 is the same thing as 100%. So that means that if we were to add up all of these probabilities, that they must equal to 1. The second requirement is that for each individual probability, it must be in between 0 and 1. Right? So we kind of looked at that probability concept. The probabilities can't be negative. A probability can be 0, right? Because it's possible for the probability to be 0. And a probability can never be greater than 1, right? Which is 100%. All right, so now let's take a look at the last problem on the handout. All right, so this is that probability distribution that we've taken a look at about a local bakery. The first problem, A, says, what is the probability of selling 15 donuts in a day? Well, they don't give us the probability for 15 donuts, but they give us the probability for everything else, right? So that means that we could actually find a probability. I could add up all of these known probabilities, and I can just subtract from 1, right? because the requirements tell us that all of these probabilities must add to B1. So this is how we're going to write that out. So this is going to equal to 1 minus all of these other probabilities added together. So 0.18 plus 0.1 plus 0.17 plus 0.36. Right. And this is going to give us a probability for finding 15 donuts. Right. So if I calculate that with the calculator, I'm basically going to put it in exactly like I see it. So it's 1 minus, and I'm going to use a begin parenthesis, 0.18 plus 0.1 plus 0.17 plus 0.36. I'm going to close off my parenthesis, and I should have 0.19. Is everybody okay with that one? All right, so I kind of set up an algebraic type, okay, even though it's not an algebra class, I kind of set up an algebraic type function to find the missing value. So this is about like the only problem where some algebra is concerned. All right. But I just added all those up and then just subtracted from 1, right? So we get 0.19. Okay. All right, B says, what is the probability of selling at least 10 donuts? So it says the probability of selling at least 10. So if you sell at least 10, that means you can sell 10 donuts, you can sell 15 donuts, or what? 16 donuts. So I'm going to add up all 3 of these probabilities. Now you're going to see words like at least and then selling like at most as we go through this. But at least 10 donuts means you can sell at least 10, you can sell 15 or 16. So I'm going to add up all those probabilities. So 0.17 plus 0.19 plus 0.36, 0.17 plus 0.19 plus 0.36 is 0.72.
So at least means I can sell more than 10, but at least 10.
That's right. At least.
So I'll go the opposite.
That's right. So I can put it this way. Like if somebody asks me for my age and I didn't want to give it to them, I can say I'm at least 20. You know what I'm saying? So that means I could be 20 or greater. Okay. All right. All right. So let's look at C. We says, what is the probability of selling 5 donuts or 15 donuts? So that's that word or again. But in this case, you either going to sell 5 donuts or 15. It won't be 5 or 15 because, first of all, there is no probability for 5 or 15. And if you sell 15 donuts, you automatically have sold 5. Okay. So you just want to add the 5 and the 15. So that's 0.1 plus 0.19, which is 0.29. So for like these probability distributions, you don't want to use that minus thing. You just only want to straight find the probabilities that you're interested in. All right.
We get on A, we get one minus, because we already had one missing, so we couldn't use.
That's right. And then in order to answer C, you had to know the probability of those donuts. Okay. All right, now for the last three, right, using that same probability, it says, what is the probability of selling 26 donuts? Well, first of all, is there a random variable of 26? No. So the probability for that is 0. Now, I had somebody in a previous class to ask, they said, well, you got 10 and 16. Could you add those two together? The answer to that is no, right? Because if you were to add 10 and 16 together, and if you were to put that in this probability distribution and add all these probabilities up, it would be greater than 1. So you don't want to add up these random variables. So since there is no probability of selling 26 donuts, that probability is 0. All right, so don't add the random variables. E says, what is the probability of selling at most 10 donuts? Well, if you sell at most 10, you'll be everything below that. That means you can sell 10 donuts, 5 donuts, or no donuts, right? So if you add all that up, 0.18 plus 0.1 plus 0.17, 0.45. So at most is that number or greater. No, excuse me. At least is number or greater. At most is that number or lesser. Okay. Now, F says, what is the expected number of donuts sold in a day? Now, the expected number is the same thing as the mean. So you're going to see expected number, or sometimes they may say expected value. All of that is the mean. So now if you think back, when we found the mean of a frequency distribution, it's like we had to find the midpoint, and then we had to take the frequencies and put one in list 1, one in list 2. We're going to do the same thing here. Right? So let me write out some steps. Put the random variable in the calculator as L1 and the probability as L2. Right, so I'm going to turn on my calculator. I'm just going to clear out my home screen. And then I want to go into Stat, and we're going to choose Edit. Right, and if you have numbers in your list, you can go to the very top, hit Clear and Enter. Right, to the very top, hit Clear and Enter. So I'm going to put in these values again, 0, 5. So remember that 15 donuts was 0.19. All right. So once you have in your random variable is list 1, your probabilities is list 2. We're going to go back to the home screen. Right, so it's second and mode, which is the quit key. And in order to find the mean, I'm going to go into the list. So I want to hit second and list. So I hit second and list, which is actually, or second and stat, which is the list function. You want to scroll over to math. Right. You want to scroll down to mean. I'm going to hit enter. And then you have to tell the calculator which list you want to calculate the mean from. So I'm going to put in list 1, comma, list 2. And once you hit enter, it gives us the mean, which is 10.81. Right. So the average amount of donuts that they're going to sell is going to be about 10 donuts, or a little bit more than 10. So now this mean, it may or may not fall as one of these probabilities, all right, but it's going to give you the average number of donuts that they sell a day. So that's 10.81.